Chapter 12 deals with chemical kinetics. We talked about this the other day in class prior to doing the lab. Kinetics is the area of chemistry that concerns reaction rates. We're looking at how fast a particular reaction goes. An example is graphite to diamond is a spontaneous reaction, although a very slow one. The production of ammonia, combustion of butane in a fire, looking at how fast that particular reaction occurs from start to finish. We're going to talk a lot about rates. Any rate of a process is the change in a given quantity over a specific period of time. We used the example the other day, again, as miles per hour. In chemical reactions, this is going to translate as a change in the amount of the reactant or in the amount of the product in a given period of time. Kinetics is based on collision theory, and collision theory says that in order for a reaction to occur, molecules must collide, and that collision is what provides the opportunity for molecules to break apart and atoms to rearrange. The more collisions there are, the faster the reaction will take place. However, just because a collision occurs doesn't mean it will result in a reaction. Not all collisions will cause a reaction to occur. For a reaction to occur, the molecules have to collide with the correct orientation. In other words, the molecules have to be arranged in such a way that will break the right bonds and form correct bonds. And there has to be enough energy in order for that to occur as well. Correct orientation, what this means is that in the example, A2 plus B2 yields 2AB. You have two A atoms bonded together and two B atoms bonded together. In order for those to react, you have to break the AA bond and break the BB bond and then form two new bonds between an A atom and a B atom. The correct orientation means that when those two molecules collide, they have to collide in such a way that the right bonds will break. And you can see in this picture, this top one is a fruitful collision. In other words, it's a collision which will result in a reaction. Because when they collide as they're arranged in that way, that will produce an AB bond. Down in the bottom picture, an unfruitful collision, in other words, a collision that does not result in a reaction, has the two molecules spaced differently. And when that occurs and they bounce off one another, it may promote the idea that this bond will form, but it would take more energy to rearrange the A and the other A and the B atom to form that new bond. So those molecules would not be aligned correctly in a way that would promote that reaction. And so the molecules simply bounce off one another. Sufficient energy. These atoms would also have to collide with enough energy to produce a reaction. So even if the species are oriented properly, there still won't be a reaction unless the particles collide with a certain minimum energy. And that minimum energy is called activation energy. It's the minimum energy that's required before a reaction to occur. This is a picture that's showing these two factors that affect collisions. You can see here AB plus C, they're reacting or moving with a little less energy than in the picture on the right. So they may collide with a certain amount of energy and bounce off. On the picture on the right, these lines are demonstrating how fast they're moving. They're moving more quickly. They have more energy. When they occur, there's enough energy within those two molecules or within the molecule and the atom to break the bond, the AB bond, and form a new BC bond. We use energy diagrams to show how that energy changes as a reaction takes place. The graph on the left is showing you the reactants that are below the products. In other words, the reactants have to gain energy in order to get up to the product energy line. So that is an endothermic reaction. The x-axis is showing us the reaction pathway on both of these graphs. The reaction pathway just means that as the reaction is progressing from the reactants to the products, how is the potential energy changing? On the right-hand side, the reactants are above the products, so there's energy that will be released as the reactants become products. And that energy released is then showing an exothermic reaction. Now in both of these, you can also see the activation energy. The activation energy is given as the difference in energy between the reactants and the top of that bump of the graph. In other words, the reactants have to achieve that certain minimum amount of energy in order to react, and then once they do, they come back down to form the products. The activation energy is the amount of energy that then those molecules have to get over the bump and form products. This part here is called the activated complex, or also can be called the transition state. And that's the point right in the middle of the reaction where the reactants, the bonds have just started to break and reform into the products. The graph on the left, being an endothermic reaction, has this enthalpy change, energy between the reactants and the products. That would be energy that's needed to be taken in, so that enthalpy change would be positive. On the right-hand side, we have, again, the enthalpy change from the reactants to the products. This would be given off, so this would have a negative enthalpy change. You should be able to identify the difference between an endothermic and an exothermic energy diagram. You should be able to label the enthalpy change, label the activation energy, and label where the transition state or the activated complex is. If the particles collide with less energy than the activation energy, they just simply bounce apart. And the activation energy serves as a barrier to the reaction. Only those collisions which have energies equal to or greater than the activation energy will result in a reaction. Remember that adding a catalyst will speed up a reaction. How does it do that? The catalyst provides an alternate pathway for the reaction. And you can see this in this energy diagram, where the blue line is showing the difference between the reactants and the products in an uncatalyzed reaction. And the red line is showing the same reaction with a catalyst. And when the catalyst is added, it provides that different energy, which lowers the activation energy, although you see that the reactants and the products are starting at the same point. We have the reactants and the products here for both reactions. But when the catalyst is added, the activation energy is only this much, rather than this much without the catalyst. There are three factors that will affect reaction rates because they affect the frequency of collisions. Remember, the theory is that a reaction occurs when a collision happens. So the more collisions there are, the faster the reaction rate will be. And these three things will affect how frequent the collisions occur. And those are increased concentration, increased surface area, and increased temperature. Three things that you saw in the first lab for this chapter. The next part of these notes deal with reaction rate specifically. Reaction rate is the change in concentration of a reactant or product per unit time. So for the reaction A yields B, rate can be defined as one of two things. It's the change in the concentration of A over time, so how fast the A decreases in concentration, or the change in concentration of B over any period of time. And since this is yielding B concentration of B will increase. And that's why you see the negative sign when we're talking about A. Stoichiometry will determine the rate of consumption of reactants and the generation of products. In other words, we can use the coefficients in our mole ratio in a balanced equation to give us a relative rate of consumption versus a relative rate of production of a product. So for example, 2NO2 yields 2NO plus O2. If 0.5 moles of NO2 react in a 2-liter container per second, what's the rate of consumption of NO2? Well, as we saw in this slide, the rate is the negative change in concentration of the reactant over the change in time. And remember that those brackets, typically we use molarity for concentration units. In this case, we have 0.5 moles in a 2-liter container. So how many moles would we have in a 1-liter container in order to turn this into molarity? Now, that means that the NO2 changes in molarity by 0.25 molar per second. And since it's being consumed, we could say that the rate is negative 0.25 molar per second. Using the word consumption is also saying that it's going to decrease by 0.25 moles per liter per second as well. Sometimes the wording in there can tell you more than the sign. And then in the generation of oxygen, well, NO2 is consumed at 0.25 moles per second. Or there are 2 moles of NO2 that react for every 1 mole of O2. So we can use that same ratio and apply it to molarity, which tells us then that the oxygen will be generated at a rate of 0.125 molar per second. And since there's a 2-to-2 or a 1-to-1 ratio between NO2 and NO, the rate of generation of NO will also be 0.25 moles per liter per second, or molar per second. In the next section, we're going to use those rates to apply to what's called the method of initial rates in order to determine a rate law for several different reactions.